That's awesome. It's okay. We'll come back to that later in office hours. Dang it. I'll come back to that later after in office hours. But to continue down on this, next we've got just more of the same with different ketones. And so the ketones can be protonated like they are here. And once they're protonated, they can take a proton on that's going to be external or internal to this one methyl group. And so the product that's going to be favored is going to be the Zaitsev product. The more substituted double bond will be the one that's more stable. So that's this one. And so hopefully you understand that. Any questions on that one? No? Okay, and then this one is actually pretty simple. It's very similar in that you're going to make your ketone that's going to be protonated, and then that ketone can get can form an enolate ion. And so, yeah, that will either have the water on internal or so it would be the secondary, the hydrogen on the secondary carbon or the hydrogen on the primary carbon. The secondary one is going to be more stable, once again, because of Zaitsev's rule. But an important thing to notice here is the ring is always blocked off. So because we have, like we talked about in Orgo 1, you can have things that are like kind of blocked by resonance or from resonance, because if you have like an sp3 carbon, like a carbon that's fully stable, it's not going to want to do like any other chemistry. It's not going to want to do delocalized electrons because it's already happy. And so even if we get this carbon to participate in our fun little enolate ion here, we still can't really force the pi bond electrons out onto this area, because for a lot of reasons, one of which is just that it would create positive charges all throughout the molecule of the ring. But more importantly, it would, there just aren't electrons there for that to happen. In order for them to fall in like this, it would, well, yeah, you would just have to create straight up positive charge, and that's just not going to happen. You can't create charge out of nothing. So yeah, that's kind of where I was going with that. This second section is a lot more simplistic. The first one was simple too. I just wanted to kind of go into detail so that you guys understood stuff better, why you're doing what you're doing. So this first section right here is working with acetate. And so acetate is just like a carboxylic group with a single carbon that's like a methyl. And so we showed here that basically when we get enolate ion formations and then we add like a bromine, the bromine will want to replace those acidic hydrogens that are on the acetate. So like the acetate has like that one methyl group that's attached to the carbon. That carbon, that carbon has acidic hydrogens. And the more you remove like bromines, the more stable it's going to become. And so basically it's like a compounding effect. And so, yeah, the reason that we're using specifically the acetate here is because it prevents like adding more than one BR. So this first section is just pretty simple on making enolate ions like you guys have been doing. And then after that, you can add a lot. Oh, wait, this was supposed to be just one. Right. Oh, goodness. That sounded weird. Okay, yeah, that's what that was supposed to look like. But the second one is just free for all. You've got all of the BRs adding. And so, yeah, the second one's going to add a lot. I actually just copied it from the first section, so these are supposed to be like that. But yeah, that's all for that's the first section. Does anyone have any questions? I overcomplicated things intentionally so that hopefully hope you guys understand stuff. No? No questions? Cool. For this recitation worksheet, it's pretty straightforward. Same thing you guys have been doing with your groups. Let's see. Ashley, I just saw your dog walk off in the background and it totally lost my train of thought. That's really it. All right, well, I'm gonna send you guys out to your outbreak rooms if there's no questions. Um, you nice group one. I'm just trying to make sure I got everybody in the right groups. And Adriana. Oh wait, I need to pause the recording. Darn it. Okay, so I realized earlier that I totally forgot to include a recording for this section of the first part of the recitation. So I'm going to do that now. For this first part, I really just drew mechanisms just to explain what hopefully you guys are already doing. Make sure you're thinking about and you're understanding why you're doing it, and you're not just doing it out of habit. So the first step of these is always going to be the partial positive on the ketone, or partial negative, sorry. I'll talk about the partial positive a lot later. And this is going to act as a base, and basically it's just going to attack and be protonated. And once you've got this here, you've got acidic hydrogens on either side that could be removed. And so really it's the exact same deal on the next one. It's just in a ring. And so hopefully that's pretty straightforward. I'm going to go help somebody in an outbreak room. I'll be right back. So back where we kind of left off, for these, I've made it look more complicated than it really is. All that really matters is that you know that there's a resonance system in this with this carbon and then out onto the oxygens out here. And so the more stable enolate ion is going to form like on the interior. So I wrote like it's the same on both sides because that's important to know that it can go back and forth. And then the exterior one is going to, if you were to do that, you would create a just left alone ketone out here, and you don't want to do that because like basically molecules really like to be stabilized and have their electrons when they're delocalized like shared amongst the largest amount of space that they can. And so yeah, that's really all there is to talk about for this one. It's important to recognize that it can go from here to here, and then what can happen is then these electrons can fall back here, these can fall back up here, and a water molecule can take this. And so that creates like a fluent dynamic of resonance throughout the two ketones. And so this is the next one. I'm going to talk about electron withdrawing groups and electron donating groups because Valu has mentioned this in the last lecture. And so that's something that we don't usually talk about until the third unit. And by mentioning it earlier, I think it'll allow you guys to kind of have a better idea of this concept before we get there. And so you won't be like deer in headlights when we get to that point. So there's electron donating groups and electron withdrawing groups. And so, excuse me, really the difference is that withdrawing groups create a positive charge that is going to be distributed throughout the ring. And that'll actually create specific like directing within the in correlation between, or coordination rather, between the withdrawing group and then like when you're adding substituents to the ring, like other substituents. So by adding withdrawing groups, they create certain patterns of addition, and electron donating groups will create other patterns. And so really to understand this unit well, you just need to be comfortable with pushing electrons around a ring. And so that's kind of what I'm going to talk about now for the next couple minutes that I have. Actually, we've got a good bit of time before they get back from outbreak rooms, and already gone around and asked questions and talked to everyone for a couple minutes. So what we're going to talk about is, if you remember, there's a partial positive on the carbonyl group. And so that partial positive is going to basically attract the negatively charged electrons of the delocalized electrons in the ring to come on out. And so when they do that, you're going to create a double bond here and a partial charge or a positive charge here. And that's not exactly very stable. So these are also called deactivating groups, because whenever you're creating positive charge from moving like double bonds, that's not stable, because it's basically like an insufficiency of electrons throughout the entire molecule, is how that kind of like manifests. And so once we've got that problem like established here, we're going to, these double bonds up in the other parts of the ring are going to recognize that, and the negatively charged electrons are going to be attracted, to the newly formed positive charge, which pushes electrons down into here, which creates another partial positive charge. And so now, if you'll notice, we've got, oops. Here, and then actually, I'm going to go ahead and cover this up. So now at this point, we've got a positive charge here, and we have taken away this positive charge that was right here, and basically that's just going to, we're going to leave it as a partial positive, because we'll come back to that, because that was where a partial, or where a positive charge was. Now, because we've formed one here, this double bond is going to want to do the same thing over again. And so it will have its pi bonds attack the positive charged carbon. And when it does that, it's going to create a brand new positive charge. And so once again, we've got the formation of a positive charge here and a double bond here. And so at this point, you've got another positive charge, and there isn't really a good way to manage that. So really, this isn't actually even going to form, but because the electrons over here, well, actually, you could have the electrons fall back up here in order to quench that. But what's important to recognize here is that when this actually, well, before I get to that point, something that I should have gone ahead and noticed was that these electrons should have been preoccupied with an alcohol. So actually, before we got to this point where we're here, this should have gone out and hit an alcohol to make it like this. And that actually really muddies the water in this even more, because as if it's not already muddy enough. I explained this a lot better when I did it originally in class than when I'm going over it now. But the point is that by having all of these partial positive charges, what you end up with is an overall deactivating effect, and yeah, I mean, that's really the main thing, is an overall deactivating effect, and the electrons are withdrawn and directed towards a certain position that we'll talk about later. It's meta. We'll talk about that another time. That's really it. I didn't explain that well, but at least now it's at least covered inside the recording. And I have spent way too much time with it. And if anyone has actually gotten to this point in the video, I'm sorry. So everybody's cleared out at this point. I've asked all or answered all the questions for office hours, and I'm just going to kind of show that this is how we do all of the chemistry here. These, I believe, are actually supposed to be done with acid, but I don't feel like there's too much to explain really. We've covered all of this a lot. Clemenson is like another way of removing all of the oxidation from like a compound. So like going from a ketone all the way through an alcohol back to an alkane. And then Wolff-Kishner is basically just adding so much base that it like punches out every single bit of oxygen in all of the molecules. And yeah. Yeah, hopefully this is all. Remember that you're going to need to use acid to add this here, and then water to remove it. Let's see what else. I mean, that's really the main things. PCC, you can use lithium aluminum hydride or sodium borohydride. This is a lithium aluminum hydride. This is the sodium borohydride. Remember, the lithium aluminum hydride is much stronger than sodium borohydride. So that's important. And then going back, oh, I'll pause it. All right, sorry about that. Now I'm going to talk about the synthesis problems. Everybody nailed these. I guess they weren't as hard as like I thought they could have been. Some people wanted to work them with a Grignard. You can do that. I am not going to show you how, just because that's not really the most efficient way. Yeah. So the first one, really, for these, I just start out by looking for like what are they changing between the starting material and the ending material. And for that one, really, you're just adding an anti-Markovnikov hydroxyl to the end of a brand new carbon. And so what can when we do that, we can just think about like ways in which we can get from this point to something that looks more like this. And to do that, I just thought of doing like what we've been doing with creating ketones. You use like a little bit of mercury here with sulfate, and then sulfuric acid. And that'll get you all the way to the ketone. And then once you've done that, you can just use a Wittig, and that's just going to replace the oxygen with a carbonyl, or not a carbonyl, a carbon. And from that double bonded alkene, you can just do anti-Markovnikov addition and add another hydroxyl group. And so yeah, that's all for that first part. Second part, we're just adding an acetyl group. You realize that you're going to have to be doing something Markovnikov style, because you're protecting a ketone that is secondary. So it's right in from the primary carbon. To start this, really, I just would once again be thinking about using a Markovnikov formation of a ketone from a triple bond. And so to do that, actually, I don't even think we used, but yeah, we did. We started out with a triple bond last time. So both of these involved triple bonds and this reagent right here. So it's important that you remember you got to use two equivalents of the sodium amide reagent. And so what that reagent's going to do is reduce both of these bromides off, and with it take hydrogens. And so once you've done that, you're going to have an alkyne, and your alkyne can get oxidized into a ketone. From the ketone, you're just going to do your normal protecting agent with an acetal and an acid. So yeah, that's all for the second one. And then the third one here really is just a matter of working backwards to do it like most simplistically. You'll notice that you're adding a carbon here and a hydroxyl. And so when I see that, I automatically think of the product of doing some type of ketone and some type of ketone and a Grignard reagent. So really, you're going to know you're going to need to get to this point here, and you know you're going to have to add a Grignard reagent with a single methyl on it. And so it's just a matter of working back from this product right here, or this material. So the first step of working back from there is that you know you can make an alcohol. So just use PCC. And then from here, I like to then just punch it all the way back to the start. And the start for this one, you're just going to want to use something to create some type of, I guess, just hold on the molecule. It's not a very reactive molecule as methyl cyclohexane. So really, you're going to want to use radical bromination and then eliminate it. We just used ethyl oxide for this with some heat. And once we've done that, you can just use anti-Markovnikov addition of a hydroxyl group. And that's all stuff that we've covered in Orgo 1, so hopefully it's pretty like intuitive. You've got that stuff down. And then from there, we'll just move on to doing PCC. And yeah, it all connects. I think that's pretty much it for this recitation. So yeah, if anyone has any questions from the video, you can shoot me an email. My email is, actually, well, this is going online. I probably shouldn't do that. Leave a comment and I'll get back to you. Oh, it's still recording.